Okay, so last time we talked about group rings and about nilpotents and zero divisors in a commutative ring. So let me just recall. So A in R, where R is a commutative ring with unity, is a zero divisor if need of this comma, if A times B equals 0 for some B in R, B not equal to 0. Yeah, and A in R is nilpotent if A power n equals 0 for some power of A is 0. Yeah, and greater equal 1. So, okay. So we saw what a zero divisor and what nilpotents were. So we saw some examples as well. Yeah. So today we'll talk about reduced ring and integral domains, which so one should think of zero divisor as a bad property, right? So you are multiplying something and getting 0. So those things doesn't happen in I mean, unless A is 0, that is. So for non-zero element to be a zero divisor is some sort of a bad property. For instance, it doesn't happen in the ring of integers. And similarly, nilpotent is sort of a bad property. So we want to find rings which don't have, so we want to define rings which don't have these bad properties. Yeah. So the first is reduced. So let R be a commutative ring with unity. It is said to be reduced if it doesn't contain non-zero nilpotents. And then so this is so you don't want anything nilpotent other than 0. So such rings are called, such commutative ring with unity are called reduced ring. And then a ring R is said to be integral domain if it is a commutative ring with unity and it does not contain any non-zero zero divisors. So in other words, every non-zero element of R is a non-zero divisor. Yeah. So last time we also saw that nilpotents are zero divisors, and we also saw that units in a ring are non-zero divisors. Yeah. So units have this property that if A times B equals C, then B equals C. Yeah. So this property is true for a non-zero divisor as well. Okay. Sorry. So this thing is true for. So this property, the way I've written, is not correct. So this property, yeah. So this is not right. So let me just cross this out. Yeah. So so this is true for integral domains. Yeah? So that is what I wanted to write. So so if R is an integral, so we'll see why this is not true since I wrote it down. So if this is the result. If R is an integral domain, then AB equals AC implies either A is 0 or B equals C.
This is even true for A belonging to R, such that A is non-zero divisor, right? Because A of A into B minus C is 0. That implies since A is a non-zero divisor, then B is equal to C. So this is true, right?
Yes, so this is okay. Yeah. A is a non-zero divisor. That means yeah. So this was okay. So I don't know why I got worried. Sorry. So this is fine. So let me. Yeah. So this is yeah. This is okay. You're right. So So this is fine. So let R be a commutative ring with unity and A belongs to R, be a non-zero divisor, then AB equals AC implies B equals C. In particular, if R is an integral domain, then this happens. Yeah. So let's. So anyway, we are planning to put down a proof. So this is the proof is goes this way. So we are given AB equals AC. Yeah. So this implies A times B minus C equals 0. Yeah. By the distributive law, and this implies B minus C equals 0, since so here is where we are using A is a non-zero divisor, since A is a non-zero divisor. So A is a non-zero divisor means you multiply with something non-zero, then it can't become zero. Yeah. If there was some non-zero element such that you multiply with A and it becomes zero, that means A is a zero divisor. So since A is not a zero divisor, it precisely means B minus C equals 0, which implies B equals C. Yeah. So this of course holds for units. You just pre-multiply. If A was a unit, this is straight. This is you just left multiply by A inverse both sides. But this is also true for non-zero devices. Okay. And in particular is obvious. So if R is an integral domain, then AB equals AC implies, so if A is non-zero, then of course A is a non-zero divisor, and then you can use AB equals AC imply, and A is not equal to 0 implies. So this by the way, precisely this statement, this implies, this precisely means that if this is statement holds and negation of this holds, then this must be true. Yeah. So these two are equivalent in logical sense. So this implies B is equal to C. So either A is equal to 0 or B equals C. Okay, make sense? Okay, good. So this is the nice property of a non-zero divisor. Yeah. So if you have a non-zero divisor, you can do cancellation. So cancellation is allowed by a non-zero cancellation. Property holds. So we are used to this cancellation property, and that holds for a non-zero divisor. Okay, so I've written down some examples. So what do we know about Z? Is it a so Z is a reduced string, right? It's in fact an integral domain. Yeah, so it's an integral domain. So of course, okay. So one trivial observation. Maybe I'll make it on this side. Integral domains are reduced strings. Right. This follows from what we saw, what we argued last time, that nilpotents are zero divisors. Yeah. So if a ring does not have any non-zero divisor, it does not have any non-zero zero divisors, then or every non-zero element is a non-zero divisor, then it cannot have nilpotents. Yeah. So this is obvious. So Z is integral domain, and hence it is also reduced. What about Z mod NZ? So that's an interesting example to analyze. So it will depend upon n, right? So when is Z mod NZ an integral domain? For what values of n?
Sir, if n is prime.
Yeah, so for n prime, Z mod NZ is an integral domain. Yeah, sorry, so integral domain.
Sir, if n equal to 1, what can we say? Like it's
Then
the trivial ring.
It's a zero ring, yeah. So
Yeah,
so when yeah, so maybe I should have said somewhere in the definition of. So when we say it's a commutative ring with it is a non-zero commutative ring. Yeah. So we are always assuming it's a non-zero ring. It is a non-zero. So if n equals 0, then you get a non-zero. So that means the multiplicative identity and the additive identity are different. Yeah. So when n is 1, this is out of question. So this is out of discussion. And when n is prime, then we know that this is in fact a field. So every non-zero element is a unit, and hence it's a non-zero divisor. What about the converse? So so in fact even the converse is true. Okay, so that means if n is not a prime, then it's not an integral domain. Yeah. So and not a prime. Yeah. So okay, maybe this space I can use to explain further. Yeah. So okay. So n not a prime. So this is one bullet. This is second bullet. Then then what can we say? And then Z mod NZ is not an integral domain. Why is that? So say n is p times q, where p and q are positive, so greater than 1, yeah, then p and q are the class of p and class of q, both are going to be non-zero elements of this thing, yeah, because q is both p and q are strictly less than n, yeah, because you're assuming both p and q are greater than 1 and strictly less than n. So they are non-zero elements, and if you multiply them, their class becomes 0. Yeah, so this is also trivial. So it is not an integral domain. Yeah, and then finally, so when is this? When is this a reduced string? So of course, if n is prime, Z mod NZ is an integral domain, and hence it is reduced. But are there other rings, other n for which Z mod NZ is reduced?
n is square free, then.
Yeah, so if n is, for instance, 6, so is Z mod 2Z times Z mod 6Z, then you can show that it doesn't have nilpotence. Yeah, so so maybe this I'll put it as a, I'll see if I want to put it as a homework or an exercise. So so this requires, I mean, one direction doesn't require the other direction. Yeah, so it's not difficult. Yeah, so Z mod NZ is reduced if and only if n is square free. P square does not divide n for any prime p. Okay, so this is what it means to say n is square free. Okay, so you can get some of the rings, naturally occurring rings, could be reduced and could be could have zero divisors, like maybe reduced but has zero. Like it could also have nilpotents. Yeah. So Z mod and Z could have nilpotents. Similar. So what about ZX? Is this integral domain or are reduced?
It is an integrator.
It's an integral domain, sure. So how do you show that it's an integral domain?
So taking the leading coefficient.
Yeah, so you take two polynomials. Yeah, so if you multiply two polynomials, whether it's Z or Q, it doesn't matter. Then the degree is going to add up. Yeah, to if you take two non-zero polynomials. So by just looking at the degree, you can say that the degree is going to be, so if it is degree 0 to degree 0 polynomial, that means it's constant, and there we know that the product is non-zero as long as both of them are known. And if both are non-zero polynomials, then also it's okay. Yeah. So one of them is a non-constant polynomial, then the degree has to be at least that. So we'll see this when we study PID and UFD, etc. in more details. So we'll see something stronger than integral domains. So, but these are integral domains. Yeah. So basically, the degree can't go down if you take the product of two polynomials. So valuation ring was homework, so maybe I'll not talk much about it, but of course it's a subring of a field, right? By the definition of valuation ring, is subring of a field, right? So this is this is one observation which we can put down here. R an integral domain. And R1 a subring of R. Subring here means it has to contain multiplicative identity of R. Yeah, so a strong sense, so that it is a ring with unity and so on. Okay, so R1 is a subring of R, then R1 is an integral domain. Right, so this is obvious from the definition of integral domain. Right? So if there exists B in R, so take any non-zero element in R1, then it's of course a non-zero element of R. So you multiply with any non-zero guy in R, then it remains non-zero. So of course, if you are multiplied by some non-zero element in R1, it will remain non-zero. Yeah? So every non-zero element of R1 is also a non-zero divisor. So that tells you that valuation rings are integral domains. Okay, so I'm just going through some of the rings which we have studied. Okay, makes sense, everyone, so far? Any questions before I go further? So sometimes I feel like I'm going a little fast, so that's when I slow down and ask questions. Ask whether you have questions. Okay, so there's nothing in the chat. Okay. So okay, so now next is this Z square. So what do you know? What do you think about Z square? Is it an integral domain, a reduced ring?
So it is
Sorry, this is giving me a bit of trouble. Yeah. So what do we know about z square?
So it would be reduced, but not an integral domain.
It's certainly not an integral domain. So what is a zero divisor? So we know that 1 comma 0 is a zero divisor. Yeah. So 1 comma 0 since 1 comma 0 times let's say 0 comma 1 equals 0 0. Yeah. So it's not an integral domain, but is it reduced?
Yes, it's reduced.
So this is indeed reduced. So you can just check that a comma b, if you have something a comma b, its nth power is just a small component wise multiplication, right? So a power n times b power comma b power n. So if one of these a and b are non-zero, then this is non-zero. So if this is so maybe I'll just write it this way. So this implies AB not equal to 0. Yeah. And then this is a somewhat crazy ring. So this was continuous functions on 0-1 interval. Yeah. So set of all continuous real valued continuous functions. So R valued, let's say, continue. So it doesn't matter whether you want to take it R valued or C valued, but let's just fix real valued continuous function on 0-1. So what do you think about this guy? Is it a reduced string or a integral domain?
Reduced is not integral.
So okay. So again, so let's just check reduce. So let f be an element of C01. Yeah. So it's a continuous function on the interval 0-1, and if we know that f power n equals 0, that means fx. So we know the multiplication is sort of in some sense component wise. Yeah. So this is f power n is identically the 0 function. That tells you that fx whole power n is 0 for all x. Yeah. But R is reduced string. Yeah. So that tells you that fx must be 0 for all x. Yeah, which implies f is identically 0. Yeah, so this argument tells us that C01 I don't know why this is cut. This tells us that C01 is reduced. But it's not an integral domain, so someone different
Or
person
for some interval take 0, for the rest of the interval take fx is equal to x. Then for the non-zero for the interval for which you took non-zero values, take 0 again, and for which just take 0, and then for the interval for which you took 0, just take any non-zero values. So something like 0 and x, from 0 to half, x from
so,
half to 1, and
yeah,
just
so
reverse it.
I'll just graph it. Yeah, so maybe f1 you can take it to be, so this is 1. So f1 you can take it to be this function. I mean a function whose graph looks like this. Yeah. So this is a non-zero function, and so f1 and f2. So you can write it explicitly. f2 you can take it to be, so maybe you just put 1/3 here, so that you don't even have to worry about much. 1 here, and then you put some function like this. Yeah, so both are continuous function. Yeah. So this is still okay, both f1 and f2, and f1 times f2 is identically 0. Yeah. So this says that this is not an integral domain. But there is something bad about this function. Yeah. How about if I impose that this is differentiable? Is it still okay? Is it still not an integral domain?
Yes, sir. We can smooth the curve over there, like x square or something like that.
So like we have studied about Uddison's lemma, like we can have differential over this region, we can smoothly do this.
You have already studied about Uddison's lemma. This is you have already done topology course, is it?
No, we did Uddison's lemma in Ulyss 2.
Uddison's lemma in analysis course. Okay.
The Urison we did was about continuous function, not differential.
I said no, we can do it also differentially. Differentiability.
Yeah, so this is indeed true, but it's slightly it takes slight bit of work. But one can now actually give an explicit function, so you can try to do e power minus 1 over x square or something like this. Yeah. So this will be for yeah. So if you graph it, I think fx you take. So you need a function which is differentiable and it looks like this. Yeah, so it's 0 at in some interval, right? So you take, so there is some explicit way of doing this, and so this is for x. So what is the derivative at x equals 0?
It can be defined over here. So
Uh,
if we do it like in the same case as Herschel pointed out, if we do it like x minus half whole square, instead of an x minus half line, we do x minus half whole square.
Yeah, you can smoothen it out that way. So this one will give you C infinity. Yeah, so differentiable infinitely many times. For twice differentiable, you can just do that squaring thing, yeah, and it will work out fine. But this will also you, so for x less than equal to 0, you put it 0, and for x greater than 0, you put this thing. So you can show that, so the derivative of this function is, so this I learned it when I was in undergraduate or something. So this trick in analysis, not in algebra. So I thought, okay. So if you compute the derivative, you get e power minus x squared, and the derivative of yeah, so maybe not 1 over x squared, just x squared is fine. Minus x squared. So then this is then it's not continuous at x equals 0. X equals 0, you get, but it's okay. So x equals 0, you get the value 1. Yeah, so I'll make one function which is flat. That is all we need. Yeah. So let me just try to work this out. So So the derivative of this is e power f prime x is 2x times e power minus x square. Yeah. So as x approaches 0, the derivative is actually 0. Yeah. And this is a continuous function. So so it looks, the graph basically looks like this. So here it is going to be 1, and then it decreases. Yeah, but it does it in a continuous way and differentiable way. Okay, so it's C infinity function, and this is how it looks like. So you just have to subtract fx minus 1 and move it a little bit to make sure you get the right example. Okay, so even for C infinity, this will be a will not be a integral domain. Yeah, but it will be a reduced string. Okay, but so these are so even if you take the nicest, so the reason I'm saying is even if you take analytically the nicest function, you don't get a right very nice ring, which is an integral domain. But if you take only polynomials with real coefficients or even complex coefficient, and then what you get is an integral domain. Yeah. So that way polynomial rings are, so they are a special kind of functions. You don't allow all kind of functions, polynomial functions. Then that ring is much more well behaved than these kind of things. Okay. Okay. So this was about reduced ring and integral domain. So let's shift our discussion to, sorry. Yeah, so last example, I guess is getting hidden. Oh, it's okay. Yeah, the example is still there. So this is reduced and it's not an integral domain. Okay, so now so is this visible, or should I make it slightly bigger for those who have smartphones? Okay, so I guess this is okay. So let R be a commutative ring. So now I want to define what is called quotient rings. Yeah. So whenever you have a ring and an ideal in it, so R is a commutative ring with unity, and I an ideal of R, then there is a ring which you can define, which is denoted by R mod I. So remember, R is a commutative ring with unity. So R is a ring means R with plus is an abelian group. Yeah. And I is an ideal means I with plus is also a subgroup of R. So R mod I as a group under addition makes sense because it's a subgroup of a abelian group, and hence it's a normal subgroup. So you can always take quotient. So this gadget R mod I as an abelian group makes sense. Yeah. So then R mod I with the usual addition. So the usual addition meaning addition as in the quotient of a group by a subgroup, and this was the usual addition, right? One quotient you want to add with the other quotient, then you just apply the group operation and then look at the corresponding quotient. Yeah. So from group theory, we know that this is well defined, and the multiplication given by this. So this one has to show that this is well defined. One has to check that this is well defined because we are looking at cosets. Yeah. So one has to check that this is well defined. But once you show that it's well defined, then this triple. So this is not just a definition; it's also some proposition. So it's also asserting something. Then and then this triple is a ring. Moreover, the map. So it's going to be again a commutative ring with unity. So it may be 0 here in this case. Yeah. So if I equals R, then it will be the 0 ring. Moreover, the map Q from R to R mod I is a ring homomorphism. Okay, is a is a surjective ring homomorphism. So is a surjective ring homomorphism. So the ring, this ring R mod I is called the quotient ring of R. Quotient ring of R by the ideal I. I mean, we just say it's R mod I, yeah. But if you want to say it more explicitly, by the ideal I. And Q from R to R mod I is called the quotient map, yeah. Quotient homomorphism or quotient map. So okay, so what is the proof? So what are the things we have to prove? So we have to check that dot is well defined, and then we'll have to check all the ring axioms. Okay. So some axioms are clear. R mod I plus is a abelian group is clear, but one has to check associativity and so on. So we'll check some of the details, but and then we will eventually check that, and then we will also check that Q is a ring surjective ring homomorphism. But maybe some are some things I'll leave it as an exercise. Yeah. So let's first check that this is well defined. So this is similar to the addition case. Yeah. Defined to be AB plus I is well defined. So what does it mean to say this is well defined? So that means if you take another coset representation for A plus I and another coset representation for B plus I, then you multiply them together, then you get the same guy. Yeah. So I let's say A plus I equals A prime plus I, and B plus I equals B prime plus I. Then we want to show that AB plus I is same as A prime B prime plus I. Yeah, so that will prove that this is well defined. So maybe not I, but maybe this is the claim and this is the proof of the claim. Okay. So the statement implies A minus A prime belongs to I. So the two quotients are same, means this, and B minus B prime belongs to I. So now, so that tells you that A minus A prime times B belongs to I, or maybe I'll do it in one step rather than doing it in too many steps. Yeah. So that will be AB, and yeah. So this is okay. So plus A prime times B minus B prime belongs to I. Yeah. Because this guy is in I, you multiply by any element of the ring, it remains in I. This guy is in I, so this guy is in I. So you multiply any element of I with an element of a ring, it remains in I. So their sum is in I. Yeah. So so you get that this element is in I, and what is this element? This is same as AB minus A prime B plus A prime B minus A prime B prime belongs to I. So this cancels out, and that tells you that AB minus A prime B prime belongs to I, which implies AB plus I equals A prime B prime plus I. Yeah. So this shows that this is indeed well defined. Dot is well defined. So associativity is clear from the fact that multiplication in R is associative, right? So A dot So associativity, I'll just leave it as an exercise for you if you can't see it immediately. Associativity exercise is trivial, easy exercise. Yeah, so it's just observation. So this times C dot. So if in this formula, if you put this times C dot I, then you'll get AB then multiplied by C, and that's same as A times B times BC. Yeah, so that is what goes on there. And for distributive, maybe we will check. So they all boils down to a property in the ring. Yeah, so maybe something we should check. Yeah, so let's just check one distributive law. So distributive axiom: A plus I dot B plus I plus C plus I. Maybe I should write it this way: C plus I. Anyway, sort of somewhat mixing of notation is there, but it's okay. So we want to show that this is same as A dot B plus A dot C. Yeah. So this is this is same as by definition. This is A plus I B plus C plus I, and this by so this is the addition in this and the sum and definition of this circle plus, and the definition of this circle dot is A B plus C I plus I. But this by associativity, by distributive law, so by ring distributive axiom in R, this is same as AB plus AC. So this particular element, A times B plus C, is same as AB plus AC, and then plus I. Yeah, and then we work backwards. Yeah, so this is same as AB plus I AC plus I, and this of course is same as A dot A plus I. Okay, so you know what I'm trying to do. Yeah, B plus I plus so this is the ring addition. Maybe I'll just throw in some bracket to make it clear. A plus I dot C plus I. So this is the addition in the quotient ring, and this is the addition in the proposed multiplication in the proposed quotient ring. Okay, so this checks the distributive law. Okay, and then you can check the commutative, the fact that is commutative is also similar. Yeah, so both associativity, commutativity, etc., they are all similar. So this proves that R mod I is indeed R mod I plus dot is indeed a commutative ring, and it is also unity. It also has unity. Yeah, so one check 1 plus I is the multiplicative identity. So again, that also follows from the same. So it's basically follows from the definition of dot circle, yeah, multiplicative identity. So it follows from the definition of multiplication in the quotient ring. So it's a commutative ring with unity. So So maybe I'll just write down what all one has to check. Okay, so yeah, so I've already written some examples. So maybe I'll just write it here. Yeah. So for some reason I had decided not to go below this line, but it's okay. Yeah, so similarly check other axioms and similarly check other axioms. Yeah. So we should still check that this is a ring homomorphism. So let's just check Q from R to R mod I, which sends A to A plus I. Yeah, so A plus I is essentially, it's a coset. So I mean, as in group theory, you may have seen that another notation for this coset is sometimes A bar, yeah, equals A bar notation. So sometimes, so this becomes tiring, so people start writing A bar sometimes. Yeah, so we'll soon start writing A bar as well. But this is so Q in group theory, you must have seen that Q is a group homomorphism. Q is a group homomorphism. This is from group theory, which you already know. So I'll just check for multiplication. Actually, the proof for both of them is same. So Q A times B is, or which we have already done in some sense, AB plus I equals A plus I dot B plus I, which is same as Q of A, Q of B. Yeah. And it is surjective as follows from group theory. Yeah. So group theory already tells you that it's a surjective group homomorphism. So that completes the proof of this proposition and defines the quotient ring. Okay. Any questions before I proceed to examples? Okay. So maybe we are before I proceed to examples, let's take a break. So maybe we'll gather in 3 minutes. Yeah. So we'll take a 3-minute break and then we'll come back again. Okay, so let me just pause this.
Sir, you are muted.
Sorry, so I went through a lot of things without realizing I was muted. So let me just repeat myself. Yeah. So I want. So you have got. So now everyone can hear. Yeah. So let me just go over this again. Most likely, even in the recording, it would seem like I'm just rolling on the screen and not speaking anything. So okay. So this is the example. Yeah, so first I talked about this chat, which I should again mention. Yeah, so this, so the two comments which were made, one by Shubhankar and the other by Sandeepan, they are correct. So if R is indeed an integral domain, then Rx is an integral domain. And if you take a ring of functions from any set to a reduced ring, then this new ring you get is indeed a reduced string. Okay, so this is now so the same proof which we did for integers or for ring of continuous function. They work here as well. Okay, so now getting back to this examples. Yeah, so this. This map n going to class of n is the quotient map, and Z mod nz is the quotient ring. So here the ideal is nz and the ring is Z. Okay, and this so you can check from the definition that these things are okay. Now the other other set of examples are these guys. So here the ring is qx, and you can take any ideal. So I've taken this set of sort of similar looking ideal, meaning they are all generated by the same element in these three cases, x square minus 2. But and this ideal is in qx, yeah. So it's a smaller set, and you go as a set is smaller, and then you take the quotient. Then what you get is so we will see that later on that this is indeed isomorphic to q square root 2. Okay, so it is so this, remember, is a sub ring of R, and hence it has to be a field. So this tells you that this has to be an integral domain. Okay, so before so actually I want to so maybe I'll say something about this map, yeah, for example 2, and then we will work, so that will tell us about example 3, 4, and so on. Yeah, so let's just discuss example 2. So first of all, this so we showed that this map Q is indeed a surjective ring homomorphism. So what is the kernel of this surjective ring homomorphism? So the claim is the kernel is in fact the ideal I itself. Yeah. So and this will show that every ideal is a kernel of a ring homomorphism. So this follows from the fact that kernel Q, the ring homomorphism which we defined, is the ideal I. Okay, so let's just see this. So of course this follows from this fact is obvious. Yeah, then of course every ideal is a kernel of a ring homomorphism. You just take R the ring, I is a given ideal, then you just cook up, then you construct this ring R mod I, which comes with this quotient ring homomorphism, and the kernel is precisely this ideal I. Yeah. So we already saw that a kernel of a ring homomorphism is an ideal, and the converse is also true. So of course, let A belongs to I, then we will show both inclusions. Yeah, so A belongs to I, then Q of A by definition is A plus I, which of course is same as 0 plus I, yeah, because A belongs to I. So implies A belongs to kernel Q. Yeah. So A is contained in the kernel, and the converse is also true. So so you can sort of reverse the whole process. So A belongs to kernel Q implies QA is 0 plus I, which implies A plus I equals 0 plus I, which implies A belongs to I. Okay, so the kernel of this this guy is indeed I. Yeah. So now let me tell you about this ring homomorphism. So the more rigorous way of doing this is using isomorphisms theorem. I think today we won't get there, but I'll sort of use those isomorphism theorem and and uh, and prove it for you. So some of this doesn't get erased, but okay. So what is the so let me define a map. Um, um, so I want to show that qx mod x square minus 2 qx is isomorphic to q square root 2. So what do we do? So we look at this map qx to q square root 2. So to define a ring homomorphism from a polynomial ring to something is very easy. Yeah. So you just have to decide where x has to go. Yeah. And then the rest is okay. Yeah. So it's like evaluation map. Yeah. So I'll say fx typical polynomial here will go to. So I want to send x to square root 2. Yeah, so I'll send it to f square root 2. So this makes sense in this ring, yeah, because this is a smallest ring containing q and square root 2. And this is a polynomial with rational coefficients. So square root 2, you can take any number of powers and that will land in this ring. Okay, so this is well defined. Looks funny. This is well defined. Yeah. So this is instead of q, let me call it phi, so that it sort of distinguishes with from that that ring, that map. Okay, let's call this phi. Okay, so we have this this thing and this ring. So this map. So one checks that phi is a ring homomorphism. Yeah. Phi is a ring homomorphism. Why is that? Because let's get rid of this line. So you just check that. So fx plus gx, when you evaluate it at square root 2, is same as first adding and then evaluating. So first evaluating and then adding is same as first adding and then evaluating. And similarly with product. Yeah. So phi is a ring homomorphism. And what is kernel of phi? So maybe this is something one has to check. So we'll do this slightly more rigorously once in the next class when we do isomorphism theorems. And what is kernel of phi? Kernel of phi is those polynomials which map to 0. Yeah. So what are those polynomials? So first thing is x square minus 2 is indeed such a polynomial. Yeah. So if you look at x square minus 2, this So x square minus 2 belongs to the kernel of phi, because if let's call this gx, yeah, so g of square root 2 is 0, yeah, because square root 2 whole square is 2, and 2 minus 2 is 0. So this implies so this statement basically implies that gx is in the kernel of phi, yeah. So and from here it follows that the ideal x square minus 2 times qx is contained in kernel of phi, yeah. So this is contained in kernel of phi. The second part is to show that the kernel is exactly phi, yeah. So that requires some work. So yeah, so that will come even later, yeah. So that requires thinking of qx as a PID, so or a Euclidean domain, yeah. So the point is given any so remainders theorem, yeah. So remainders theorem is something which you know, or at least you must have seen the statement in high school, yeah. So if fx is any polynomial in qx, then you can write fx as so gx is our x square minus 2, so gx times qx plus rx, where rx is some polynomial of degree 1 or less than 1. Degree rx is less equal 1. It has to be strictly less than 2, yeah. So this is less equal 1. So so we'll talk about this as well when we, so I'm sort of going ahead of and showing you something which you can do after learning about PID and Euclidean domains and stuff. So that tells you that R has to be a linear polynomial. And of course, if you so now if you plug in f of square root 2, then this is equal to 0 will imply R of square root 2 is 0, which of course can't happen for any linear polynomial with rational coefficient, yeah, because square root 2 is an irrational number. So this non-zero rational polynomial. So this tells you that Rx must be 0. Yeah. So from this you can so if f maps to so f of square root 2 is 0. So if f is in kernel of phi, then f of square root 2 is 0, and that implies that R must be 0, which tells you that f is a multiple of gx. Yeah, which implies that f is in which implies that f belongs to this thing. So this argument tells you that that kernel phi is precisely this ring. Yeah. So sorry about this. So this implies kernel phi is kernel phi is, sorry, x square minus 2 times qx. Okay. So then there is this first isomorphism theorem, which says that if you have a ring homomorphism from R to I, R to R prime, then surjective ring homomorphism, then surjective ring homomorphism, then R mod the kernel of that ring homomorphism is isomorphic to R prime. Yeah, so from here, first isomorphism theorem will tell you qx mod square minus 2 qx is isomorphic to q square root 2. Okay, so this subring. Okay, so maybe I should hold on this thing for a bit. Okay. So I'll state the isomorphism theorem next time. So let's not get there. But let me just yeah. So let me just discuss other examples which are slightly easier to. So I mean here also this wasn't too bad, but I wanted to say something about the other examples. So how they are different. Yeah? So number 2. You quotiented out by this ideal generated by x square minus 2, you got integral domain. But if you do the same thing in the third example, this is not an integral domain. Yeah. So this target ring is indeed not an integral domain. So what is a zero divisor here? So if you look at the image of, so I'll put bar, I'll use the bar notation. So you can look at x bar minus x minus 2 bar, the image of the polynomial x minus 2 and image of the polynomial x plus 2. They are zero divisors. In fact, they are non-zero elements because I mean these are not in the ideals. They are small rings. They are polynomials of smaller degree, and every polynomial in the ideal has degree is either 0 or has degree at least 2. Yeah. So they are not in the ideal, so they are non-zero. But if you multiply them, you will get x square minus 2, and hence their images, their product is 0.
So shouldn't it be x minus root 2 and x plus root 2?
X minus, sorry, yeah, you're right. X minus root 2 and x plus root 2. Yeah, that is the whole objective. Yeah. So x minus square root 2 and x, yeah, sorry. So maybe I'll write it more clearly. You look at x minus square root 2 and x plus square root 2. Yeah. So they are polynomials with real coefficients. So the point is these polynomials don't exist in Qx, but they exist in Rx. And they are linear polynomials, so they don't lie in the ideal, but their product lie in the ideal. So this is not an integral domain. Yeah, so this is not an integral domain. Similarly, this is Z. So this is similar to Q. Yeah. So this is going to be an integral domain again. Okay. So more or less the same proof will work, but will. So this is a more complicated ring than this one. And anyway, so I was planning on doing some isomorphism theorem and then getting to discuss 5 and 6. So these two we'll discuss next time. Yeah, so next class we'll discuss.
Is it possible to classify all the ideals of ZX or QX?
QX, it's easier. ZX is classify means what? I mean, one has to. So QX is somewhat simpler. So QX is easy, yeah. So let me just say you can classify all ideals in some sense. ZX is slightly more complicated. So classify, one has to understand the word properly, yeah, what it means, yeah. So as a subset, yeah, sure. I mean, given some polynomials, you just look at the ideal generated by those polynomials, but you want to say when the two ideals are same and so on. So those things are not so easy to decide in ZX, but much easier to decide in QX and so on. So ZX is a much more complicated ring than QX. QX is in some sense very similar to Z, the ring Z. So I mean, it may not look like it, but in terms of ideal theory, it's very similar to Z. but Zx is somehow becomes much more complicated. So we'll see these two examples, 5 and 6, in the next class. Okay. So maybe this is a good place to stop. So if you have any questions, this is the time to speak up. Yeah. Yeah.
So in the converse of the proof, where you prove that this is a home of like qx, the kernel equals to x square minus 2 of qx.
Yeah.
So in that, I think f of x belongs to kernel of y, right?
Yeah. So this is what
It's
I
like
want to say. So
but
so this we have shown. So let fx belongs to this, and fx belongs to kernel phi.
yeah.
Then we show that fx. Then we show that fx. So these two implies fx belongs to this left hand side. Yeah. X square minus 2 times qx. Is that what you are trying to say?
Yeah. Otherwise, you can't state that f of proof equals to 0. Right?
Yeah, exactly. So I said it in words but didn't write it. So if fx belongs to kernel of phi, then f of square root 2 is 0, and then this happens. Okay. Any other questions or comments? So you can see, I mean, it requires just to prove that qx mod x square minus 2 times qx is isomorphic to q square root 2. It requires a bunch of calculations and some theorems, which like this is the remainders theorem. Yeah. So remainders theorem. So what is called a result like qx is a Euclidean domain. Okay. And maybe so so I don't know how much I'll do about this thing, because yeah, so unfortunately to so this of course by same principle, this is same as these adjoint square root 2. Yeah. So you try to give a map to R, Rx, so to speak. R's, yeah. So or complex numbers from so this map phi, if you restrict it to Zx, yeah. So this gives you a map from Zx to q square root 2, but the image actually lies in Z square root 2. Yeah. And the kernel, again, you can show that this is so this is going to be Z square root 2. This is interesting. So this I'll tell you what this is roughly. So this is so you go so you are going mod 2 and x square minus 2. So the point is you can do it in steps. So this is Z mod 2, Z polynomial modulo x square minus 2. So this is going to be isomorphic to, let's say, this mod x square. So not naturally. So maybe I should just put it y here. Y square. So this is not a reduced string, but this guy, because y, the image of y is nilpotent, and this guy is going to be, so one has to work this out, but this is going to be isomorphic to mod x square minus 2. Yeah, so so in some sense I haven't simplified y square z mod 2zy, I should write. So the ideal generated by y square. So sometimes the ideal generated by something is denoted this way. Yeah, so I'll just use that notation. So this is isomorphic to this. So so this is yeah. So I have to think whether this is an integral domain or not. So let me just think about it. So 2 square is 4, 3 square is 9 4 square. Yeah, so this is an integral domain. So it's certainly reduced, but it's also more than reduced. This is actually an integral domain. Okay, so these things also we'll see. So I don't know if we'll see it in next class, but we'll see in this semester. Okay. But this isomorphism we'll see, and this isomorphism we'll see next class. Okay, these number 5 and number 6. Any other questions? So there is one message. You wanted to hear the third example. Yeah, so that, give me a second. Yeah. Yeah, so the third example, so this quotient ring is Rx mod x square minus 2 Rx, yeah? So, okay, let me just discuss this. So this contains, so let me just write this example better. Yeah. Can you hear me, see the board? Hello? Yes, okay. Yeah, so this third example is this Rx mod x square minus 2. So this we can do it very explicitly because the assertion is very simple. I want to say that is not an integral domain. Yeah. So what is the, so you look at the guy x minus square root 2 in Rx, yeah, and look at its image in this ring. So what is q of x minus square root 2? So this is, I mean, there are many notations here. So as using x minus square root 2 bar, but if you like, you can use the notation which is same as x minus square root 2 plus, so I'll give a name to this ideal, square minus, so that I don't have to write this time and again, yeah. So this is I say, yeah, so this is same as this ideal I. And x plus square root 2 is similarly, q of x plus square root 2 is similarly x plus square root 2 bar is one way of writing it, and the other way is x plus square root 2 plus I. Yeah. So these are elements of Rx, and I'm just applying the ring homomorphism Q to get an element in this quotient ring. Yeah. Now you multiply these two. So x minus, so that, yeah, so if you multiply these two elements, then what do you get? So you get x minus square root 2 plus I times x plus square root 2 plus I. Then that is same as multiplying these two and then putting I there. Yeah, so this is x minus square root 2 times x plus square root 2 plus I, which is x square minus 2 plus I. But x square minus 2, the ideal itself, x square minus 2 is contained in I. Yeah, so this tells you this is 0 plus I. Yeah. So that tells you that product of these two guys is the zero element of this quotient ring. Yeah? But of course, these are non-zero. Yeah, so this is not equal to 0 plus I, and this is also not equal to 0 plus I, because this ideal contains only polynomials of degree 2 or higher, and the zero polynomial. So zero polynomial has no degree or infinite degree, if you like, by convention.
So this is related to somehow the factorization of like the x square minus 2 in Rx.
Yeah,
R.
so this is precisely and this precisely happens because you can factor x square minus 2 in R, but you can't do it in Q. Okay, so that's pretty much what it is there in this example. So this is how one cooks up such examples.
So can we say that this whenever we take the quotient ring that it is in of this form, then it is an integral domain if you can factor if there exists no factorization in that ring.
Yeah, so if your ambient guy is a polynomial ring over a field, then of course you can say that. Otherwise, yeah. So we'll see some relations. Yeah. So there is we'll learn about what is called prime ideals and so on. So if the ideal is a prime ideal, then the quotient is an integral domain. It's the content. Okay. So we'll see those results. Sometimes, so factorizations, etc., work well when you have a nice enough ring. So something like a UFD, so something which will be called unique factorization domain and stuff. So we'll study. So for nice rings, your statement will be right, but we'll see many generalizations as well. Okay. So this is just the beginning. Yeah, first second week of class. Any other questions? So I hope the person who asked this question got their question answered. Yeah. Okay. Good. Aman. Okay. So let's call it a day. So I'll if there are no more questions, I'll stop the class. Yeah.